reads my "I'm here" thing. Or maybe he does. Do you?
I'd appreciate it more if you were here before the bell.
Oh, okay.
Anyway. Last time, we started into chapter 13, talking about, that's the wrong book.
Yeah, wait, what book is it?
It's biology.
Oh, we can for sure run that.
Not that I was any better at it.
Yeah.
Now, we gave you a whole bunch of different laws, and it all came together with the combined gas law. Where we can change pressure, volume, and temperature. Okay. Remember, that is the one that's going to be on the front of the test. Okay, so know how to work with that one. Okay. Remember, whatever is constant, just take it out of that. Okay, whatever is constant, just take it out of that. And that will give you whatever law you need, whether it's Boyle's, Charles's, or Gibbs. Yes?
On the homework, I have a question.
Okay, I'll go to you first.
Even if we don't get the right answer, what happens?
Like, what if you tried?
If you put a valid attempt, you will get partial credit.
Oh, good, because I'm writing all that partial
Can we
credit.
go like on?
Over like one of the comments.
What are you struggling with?
Like, no, it's just like, I feel like I know how to do it. I just need to make sure I did it right. Like, I want to for sure make sure I
We should do,
Let's do this, and then if we have time at the end, we can talk about that.
did it right. Okay.
So, the one thing that was constant in this one was the amount of gas. You can't change the amount of gas you're working with and still be able to use this, because that just changes everything. Today, we're going to be able to work with a gas law where the amount of gas factors into the calculations. So now, if you remember last time when I took off problem 53, because for whatever reason it asked a question about something that's in section 2, well, let's talk about that.
oh,
Okay. Question 53 asked, what are the standard conditions that we measure the volume of a gas? Okay. So obviously, when we change the temperature and pressure, the volume is going to change. So we've set a standard temperature and pressure that we can measure all gases at. And we can compare them at the same values. So standard temperature and pressure, we call STP. STP, standard temperature and pressure. You also might know it, depending on what kind of music you listen to, as Stone Temple Pilots. But you guys are probably a little too young for Stone Temple Pilots. So your parents might know who they are. Anyway, in chemistry, STP, standard temperature and pressure. And what that is, what the temperature and pressure are. So temperature is 0 degrees Celsius, pressure is 1 atmosphere. Okay.
That's just like, that is the same.
That's STP, standard temperature and pressure. Temperature is 0 degrees Celsius, pressure is 1 atmosphere. So anytime you have a problem that references standard conditions, you know that those are your conditions. Okay. So, and at standard conditions, at 0 degrees Celsius and 1 atmosphere, every single gas out there has the same volume. Okay. 1 mole of gas at STP has a volume of 22.4 liters. Okay. 1 mole of a gas at standard temperature and pressure has a volume of 22.4 liters. We can use that as a conversion factor with our unit multipliers. And we have an example of that. It's pretty straightforward. So example problem 5. Main component of natural gas used for home heating and cooking is methane, which is CH4. Calculate the volume that 2 kilograms of methane gas will occupy at STP. So we have 2 kilograms of methane. Now, if we have grams, can we work with that very easily in chemistry and doing calculations?
No.
What's the first thing we do with grams?
Change it to moles.
Change it to moles. Very good. So
I know how to do it.
we have 2,000 grams of methane. How do we change it to moles?
So we need to find the CH, then what is the gram?
What is the molar mass? So you're saying we need to take 1 carbon and 4 hydrogens and add them all up based off of what we find on our periodic table? Yes, that's exactly what we need to do. So we take 12.01 and 4 times 1.01, which is rounded off the problem. And what we get is 16.05. Okay. So now we have moles of methane.
That was magical.
But is that what the problem asks for?
No.
What does the problem ask for?
Yes, for the pressure.
The volume.
The volume. Same thing.
Not quite the same thing, but you know.
But like, kind of.
Just pretend.
Yeah.
Now, it does tell us that it's at STP, which means we can use this conversion factor. So 1 mole is equal to 22.4 liters.
Oh.
And that's it. When you're at STP, it's really easy. Okay. And if you do the math, it is 2.80 times 10 to the third.
Oh, so 1 mole is equal to 22.4 liters.
At STP, yes. If you have STP, 1 mole of any gas, 22.4 liters. Okay. So, What about if we're not at STP? Then we have what's called the ideal gas law. Okay. Now the book goes through and shows you how the ideal gas law was derived. We're not going to take time to go through that because, well, I doubt you care.
Oh, so we're just going to skip that?
We're going to skip the derivation,
I don't know what that would mean.
how we came to get this law.
Oh,
I
yeah,
actually
yeah.
cannot do this, but
We're definitely going to use it. We're going to use the gas law quite a bit.
oh. Oh yeah, wait. No.
No, but then we get that.
Yeah.
So, first off, we need to mention what is an ideal gas?
The ideal gas constant.
Well, just an ideal gas.
Yeah, it doesn't say that on here. So
Okay. Basically, an ideal gas is a gas that follows the assumptions made by the kinetic molecular theory. Okay. There's no volume in the particles. They don't have interactions with each other. All the collisions are elastic. Okay. In the real world, there is no such thing as an ideal gas. Okay. All gases obviously have some volume with the particles, and that right away says it's not an ideal gas. But a lot of gases behave very, very close to an ideal gas. And so it's good enough for us to use this. We will just assume that they're ideal gases. Okay. Now, these gases, even if you have one that is very close to an ideal gas, if you do extreme heat or extreme pressure, it stops behaving like an ideal gas. Okay? Just so you're aware of that, because there might be a question like that on your homework. So, but anyway, as we said, we are going to skip over how we got to the gas law and go straight to the gas law. That is the ideal gas law right there. Okay. In chemistry, we call it PIV-NERT. If you walk up to a professional chemist and ask them what PIV-NERT is, they'll tell you it's the ideal gas law. Okay. So let's break it down. 3 of these things we've already dealt with.
pressure, volume, and temperature.
Pressure, volume, and temperature. Okay. Straightforward.
Like the R rate or something.
No, R is the symbol that is representing the ideal gas constant.
Very good.
Yeah, you just read
I
that.
didn't don't tell people that.
What's wrong with reading the textbook?
Because it made me sound smart.
Reading the textbook is how you find information. Reading the textbook is an excellent idea. Yes, R is the ideal gas constant. Here's the good news.
What?
It's a constant.
Okay.
You're never going to have to calculate R. R,
Oh.
once again, is given to you on the front of the test. Okay. Here's the problem. R changes depending on what units per pressure you're using. Like I said, pressure is the one thing in science that we just can't agree on units. So there's still just a whole bunch out there. Okay. Anyway, the values of R are given to you on page 454. You will need those for today's homework. Okay, on page 454. Now, the units are in, so liters times whatever pressure unit you're doing, okay, divided by mole Kelvin. Okay. Now, whatever pressure is right there, you need to make sure that it is in the same units as whatever pressure you're using right here. Whatever pressure it gives you in the problem, make sure you pick the right constant. If you don't pick the right constant, you'll get the wrong answer. Okay. So if you're using atmosphere, okay, so if you're using atmosphere, R equals 0.0821 liter atmosphere over mole Kelvin. If you're using kilopascal, R equals 8.314 liter kilopascal over mole Kelvin. Those are the only two I give you on the test, because the third value that it gives here for millimeters of mercury, I think millimeters of mercury is the dumbest unit ever. Okay. But it's out there. R equals 62.4 millimeters of mercury over mole. Okay. So let's put them up there because we're going to use them, and I don't want to have to keep looking them up because I know them approximately, but I always still look them up. Okay. So that's R. We figured out R. What about little n? Anyone know what that stands for? The number of moles. How many moles of gas are we dealing with? Remember, we said we are now going to be able to change the amount of gas that we're dealing with. Also, notice there's no ones and twos. Okay? We're not talking about initial conditions and final conditions. We can just calculate initial conditions. Okay? So, let's do an example. The nice thing is, it really is a whole lot like Monday's class. You're going to be given all but one and asked for the final one. That's really all it is. Okay, so it's going to be more of the same like what we did on Monday. Okay. Now, example problem 6. Here we go. Calculate the number of moles of ammonia contained in a 3.0 liter vessel at 3 times 10 to the second Kelvin with a pressure of 1.50 atmosphere. Okay. Once again, we do want to use Kelvin. Celsius having 0 and negative numbers will throw everything off. Okay. So, let's fill in what we know. Well, the problem tells us, okay, we have a 3 liter vessel. So that's our volume. Okay. At 300 Kelvin. That's our temperature. with a pressure of 1.50 atmosphere. It asks us how many moles, so that's what we're looking for. So now all we need is R. Which value of R are we going to pick? One of these three. The first one. So you're guessing the first and the third, and you're guessing the second.
Yeah, involves the
Well, one of those is right.
What we did there.
So we have another vote for the first one. Why the first one?
Because it's atmosphere.
Because it's in atmospheres. That right there tells you you pick this one. Okay. Let's work it out. We want to isolate N by itself. Okay. So when we do that, we get that. Okay. And now all we have to do is put the numbers in, grab our calculator. So 1.50 atmosphere times 3.0 liters divided by 0.0821 liter atmosphere mole Kelvin times 300 Kelvin. So let's cancel out some units. Canceling out units is always a great thing to do to make sure you've done your algebra correctly. Okay, so we have an atmosphere here, atmosphere, liter, liter, Kelvin, Kelvin, because this is divided by. So our units that we're left with, 1 over moles. Does that make sense? Is that a weird unit to have, 1 over?
Yeah.
Guess what?
Would that just be?
That's just moles. Okay. If you have 1 over a fraction, you just flip the fraction and that gives you
Oh, because
the
it
answer.
would be a whole.
So anyway, so our units that we have left are moles, which is exactly what we want. And now we just throw those numbers into our calculator. Okay. And we get 0.18 mole. Okay. 0.18. Does that make sense? Should we do another example? Okay, let's look at let's just look at number 26 on page 455. So it says determine the Celsius temperature of 2.49 moles of a gas contained in a 1 liter vessel at a pressure of 143 kilopascal. So once again, let's just start writing down what we know. So we have 2.49 moles. Okay. 1 liter vessel. Pressure, 143 kilopascal. It says determine the Celsius temperature. So we're going to have to go from Kelvin to Celsius, but that's not a big deal. And this time, what value of R should we use? We're going to use the second one because we're in kilopascal. So this one, we have 8.314 liter Pascal mole Kelvin. So this time, we want to isolate T by itself. So that's going to look like this. Start filling things in. Let's cancel out our units. We're left with 1 over 1 over Kelvin. That's exactly what we want. Okay. Throw that into our calculator. And it's going to give us, so I have the answer, but it's already in Celsius. I want to do the Kelvin for you real quick here. It's nice when you have 1 liter because that makes the math really easy. What's 143 times 1?
143?
Yay!
Oh, so good.
So that gives us, let's see, 6.91 Kelvin. So we take, that's really cold, by the way. So we take 273, subtract, well, really it's going to end up being 7. So we get negative 266 degrees Celsius. So, in order to have these conditions, you have to have something really, really cold. Colder than that. So, now, sometimes the problem may ask you about like molar mass of something. Okay. Now, obviously, you should, at this point in your chemistry career, be able to go from moles to mass fairly easily. Okay. It's like what we did, you go to the periodic table. However, sometimes we like to do everything all at once. So what we can do to, speed things along we know that the number of moles, okay, the number of moles is equal to the actual mass divided by the molar mass. Okay. So we can take N and substitute it there. So our new gas law would look a little bit like that.
So what did that happen?
The small m is the actual mass, and big M is the molar mass. So what you would calculate, like we did with methane, you take 1 carbon, 4 hydrogens, add those up. Okay. So that way, if the problem either gives you molar mass or actual mass or whatever, you can throw that in there already. Can you do it separately? Absolutely. Okay. You don't have to do it this way, but if you want to do everything all in one step, you can do it that way. Okay. Otherwise, you can either do this calculation separately before or after, depending on what the problem is, and then take n and put it in. That works too. Okay. Just want you to be aware of that. Okay. Another thing that sometimes we will do with the gas law, sometimes they want to know the density of a gas. How do we calculate density? It is mass. Mass over volume. Very good. Okay. So we can take this right here and work it into this. Okay. Now we can rearrange this right here. So if we pull we can do that. We can rearrange it like that. Does everyone see what I did? Does that make sense algebraically? Here, I'll show you. So I want to rearrange to get mass over volume like that. First thing I did, multiply both sides by molar mass. And then divide both sides by RT. And then divide both sides by volume. So we get molar mass times pressure divided by ideal gas constant times temperature equals mass over volume, which equals density. So, yeah. So if you're given density, if you're asked to calculate density, you do one of those. Okay. The rest of the chapter goes into a little bit more about real versus ideal gases. We talked about that a little bit, and honestly, I'm not really going to emphasize that on the test. Like I said, there's a good chance that on your homework there's a question that will talk a little bit about that. But beyond that, yeah, I'm more concerned that you can use that equation. So let me give you your homework assignment. You can get started on that. And then if you have questions about this homework or last homework, we can look at this.